Thank you, everyone, for coming. So this is a talk about distributed tracing, microservices, and about complexity of those things. An agenda, so I will introduce briefly what distributed tracing is and why we're using it. And then I will talk about different ways of using tracing data that we found useful at Uber. Basically, there's 4 sections that I will be presenting, and then we have a time for Q&A. So just to introduce myself, as Suzanne mentioned, I work at Uber in the observability team, been there about 4 years. I primarily work on distributed tracing and our tracing system, Jaeger. It's open source. We donated it to Cloud Native Computing Foundation a couple years ago. I also work with 2 other CNCF projects, Open Tracing and Open Telemetry, which are the sort of the instrumentation side of open tracing and of tracing and metrics. I'll touch on those briefly. And also, as Suzanne mentioned, I published a book recently. This book is I had about 4 years of experience doing the tracing, so I decided to write about it, and it kind of covers a lot of tracing history, current state of the industry, a lot of different standards, and it's also a very practical guide. You can just dive in and start instrumenting the applications, and plus a lot of advice from my own experiences. And so if you're interested, you can find it from my website. Before I start, I just want to maybe take a quick poll. So I'm assuming like everyone is using microservices if you are in this room. But how many people actually know what distributed tracing is? All right, so hard to count, but I think it's roughly 40% maybe. And how many of you actually use distributed tracing in production? Okay, so it's a good amount, about maybe 10%. So that's worth speaking about, like why we're doing distributed tracing. And it's not a new thing, right? The papers on Xtrace and Dapper at Google appeared more than 10 years ago. But tracing is kind of gaining popularity recently, and in part it's because, I think, of the microservices movements as well. And so I want to cover a few trends in the industry that sort of lead to, I think, why tracing becomes important now. So one is not really a trend, it's a done deal, but as internet companies started like having to serve millions of users, basically we had to start building very complex distributed systems, scale from 1 computer to hundreds, thousands, right? And so that basically created a lot of complexity already. The other trend is as people were developing monoliths, you could scale the monolith to 1,000 hosts. That's fine. But at some point, as your organization grows, you reach a point where the monolith creates an organizational challenge. You can't deploy features fast enough because like everything is intertwined. And so people start breaking up monoliths into microservices. Which allows like a lot of different benefits, but also microservices creates like enormous amount of challenges for operating them and understanding them, which is what I'm going to be talking about. A third trend is sort of an evolution of our programming paradigms. We traditionally, well, maybe early 2000, if you had a Java server, it would run a few threads, and each thread would execute 1 request at a time, right? The logic of that was pretty simple, and if you need to debug that system, it was fairly straightforward. But then we've introduced new types of concurrency. We introduced asynchronous programming, where a single request, like think about futures or promises or event-driven frameworks, where a single request can start on 1 thread, then get paused, get put on another thread. And so if you try to debug that becomes much harder because like, where do you look for? Like, how do you look for a log, for example, from that request? And finally, when we blew that up into microservices world, that became even we created the distributed concurrency, where a single request not only jumps across threads, but across threads in different processes, different nodes. Understanding these systems and debugging them became really, really hard. not as it was before with distributed systems. The culminations of this is sort of microservices architecture, like the one at Uber, where we have over 3,000 services, and they are all in multiple programming languages. So this diagram is rendered by Jaeger is a portion of that architecture. I think nodes represent like the services, and the size of them is roughly proportional to the traffic, and edges are connections between those services, the RPC calls that they make. What's interesting is that if you click a button at Uber, a transaction can hit that architecture, which looks like this, right? So it can touch like hundreds of nodes, multiple types of services, like from different business domains. So what we do when something goes wrong in this architecture, right? Another thing that microservices architecture introduces is an increase in the number of failure domains. Because we know that like if you read any distributed systems paper, they would mention communications are not reliable, right? This is kind of the basic premise of distributed systems design. And then, well, microservices says, let's bet down on this unreliable communications and use it for everything inside our system, right? And so this number of communications increases exponentially in the microservices architecture, and that increases the number of failure modes. So in order to operate such complex systems, it's almost impossible without very strong and good observability systems into what's going on. And specifically, we can't understand what's going on in the system if we're looking at just one single node of it, right? We kind of, from the transaction before, if it touches 50 nodes, I kind of need to understand what happened along the path of that whole transaction before I can reason about what happened in the request. And so we need to monitor these distributed transactions. Now I want to touch about like what is observability, right? And specifically, how is it different from monitoring? I mean, sometimes people kind of think that observability is like a fancy name for monitoring, but I think of them very differently. Because to me, if you think about the word monitoring from the dictionary, it says, well, you decided what to measure, you decided that it's important for you to measure that, and you monitor that, right? Well, that is not the thing that humans should be doing in production, because there's so many things that are important and you need to monitor, so you just go and automate that. You put alerts on those things, right? So to me, monitoring is things that you knew a priori are going to be important and that you need to automate completely. The human should not be involved in monitoring. Human is involved once the alert fires, then you have to involve human to debug the problem, right? Whereas observability is actually observability is really an ability to ask questions about your system. And those are the questions that you don't know up front. So that's the main difference from monitoring. And distributed tracing is kind of, it's in a unique position across all observability tools that it can answer questions that no other systems can answer, right? I'm not going to read all this, but just to give a taste is that if you have a long request, like which service created a fault in that request, right? How do you find out? What if you got an alert from your business metrics saying users can't take trips on Uber, right? That's what we monitor. That's what we should monitor. That's the metric that's important to us. But how do you go from that to some service X that's actually misbehaving or having capacity issue, right? So that's what we want to be able to answer. These are the types of questions. And the last one question is kind of funny, right? But it's one of the most important ones, because if you imagine the architecture like 3,000 microservices at Uber, or any organization which has a sizable architecture, I can guarantee there's not a single person that knows what every those services are doing, right? So it's impossible to keep everything in your head. So if you are responding to an alert about the business metrics falling down, your first goal is to basically isolate where the problem is and find the person who can actually solve that problem, right? You're probably not going to know what the service X is actually about and what it's doing. And so distributed tracing is kind of in a unique position to point you quickly in that direction. And I couldn't find, unfortunately, for the slide, but there was a recent tweet from Charity Major, CEO of Honeycomb. She said, like, one of the hardest things is observability is actually not finding why something is failing, but where it's failing, right? And that's actually rings very true to me, because I've seen that at Uber with the first responders, where they just spent half an hour trying to just narrow down the problem to a service. And then once it's there, that's actually figuring out the problem becomes much easier. And so distributed tracing is very well positioned to answer these questions and accelerate root cause analysis, which is an important part in outage mitigation. So let me start just very quickly overview of what distributed tracing, how it works, right? So the idea is exceptionally simple. You have a request coming in architecture, we assign it a unique ID, and we make sure that we pass that unique ID through all the calls that that service makes and all the downstream services make. If you're using messaging, it works the same way. So while we're doing that, we have a background sort of process in each service which collects the telemetry data tagged with those unique IDs, and then sends it out to the tracing system, which allows us to reconstruct basically a workflow, the life cycle of that request. And it collects timing data, causality data, like who called whom, things like that, and all kinds of other attributes about the request, like what's the URL for a given endpoint. And so on the right side, you can see there's a very typical like Gantt chart view of the trace, where it's a collection of spans. So like I will probably be using term span, so I want to bring it up front. Span is just like one unit of work, usually like a service endpoint, but could be something smaller within that as well. And what trace is really, it's a narrative about a request. It's what happened to that request in a distributed architecture. And so let's take a look at the real example of a trace. Well, it's not quite real. It's a toy example still. So it's a Gantt chart, and we can see that on the left side there is a sort of like a hierarchy, parent-child relationships between services and operations, who called whom. And then we have a timeline, like with the time measures. Above the timeline, there is a mini-map of that whole trace, because sometimes the full trace is sort of very many pages long. So if you want to get a grasp of what it looks overall, then that mini-map shows you the kind of the total structure of it. It's specific to Jaeger, but some other tracing systems have that visualization as well. And then some of the things that tracing makes like immediately apparent is that here's a blocking transaction, right? So this operation, MySQL query, blocks all the like calls above it, right? And it's like nothing can proceed until these things. We can very clearly see that just from the layout of the Gantt chart. And then on the other hand, on the right side, we have a series of steps which look like a staircase that indicates that, well, okay, well, there is a number of operations happening, but they all seem to be happening sequentially, right? So if you are troubleshooting a specific performance issue, then that clearly points you to two places where you can potentially improve things, right? Try to reduce the SQL or try to parallelize these things. Why are they doing all in serial? I mean, there might be good reason why they're doing in serial, but in this case, like if you knew that application that there isn't, that could be parallelized, right? And finally, there's the tiny thing, there's like a red exclamation point. So when there's an error, instrumentation captures that and tags it with a span, and so we can display it. It's not very visible, but that error sort of bubbles up if you start collapsing the hierarchy on the left. So sometimes it's actually very easy to navigate from the very top one. You will get an error, you expand it, oh, the error actually moved to one of the 5 services or something, and you can drill down this way. And finally, when you click on one span, you can get into details about that span. And those details are usually very rich, right? You obviously have some timing information when it started, but you also have 2 sets of metadata called tags and logs. So tags are, well, just like some key value pairs attached to a span. And one of them, for example, is a SQL query, which could be very useful when you're investigating a problem. That it could be very detailed. You can include all the parameters of that query. And again, I mean, if you, there's like very few tools that give you that kind of information, right? And the logs are sort of just, you can think of just timed events within the lifecycle of a span, but they look like logs, just like contextually limited to the span. And I think that's like an important distinction of the tracing as a tool, is that all information in the trace is very contextual. Right? It's if that query, SQL query, it belongs just to the span, if you have another span, there's going to be another SQL query. Or the logs, they're also structured within the single span. So that's very different from the normal logging tools where you just have a stream of things and then you need to somehow filter them as to like, OK, what happened in this one single request? Even if it's on a single thread, it's kind of hard. So tracing sort of makes it a lot easier to navigate. I spoke to one of the users of Jaeger open source, and they said they kind of stopped doing logging altogether, and they log only to the traces, right? Because that allows them much like easier investigation of things rather than doing like a normal logging into elk or something. And we can also trace asynchronous workflows with this tool. Like this example was purely RPC, right? But if you have a system based on Kafka, in fact, when I was writing my book, I had a chapter about exactly that, so I kind of decided to put it in the slide. So there's like this mock application tracing talk, which is like online chat application where you can chat with someone, and then you can also put like a Giphy and some title, and it will pull an image, right? Very standard thing. And so the architecture of that application looked like this. You have a JavaScript front end, an API server which receives the messages, and that's what represents the actual trace, like the transaction coming into the API service. And then it deals with like the Redis is used to store the messages. Kafka is used to communicate between all the components within one, right? And then making calls to the Giphy as an external part. And so if you take the trace, that's what it looks like, right? So very similar to the previous RPC trace. On the left, we have the hierarchy of sort of operations happening in an order. And then this span, I don't know if you can read that, but it says like storage service receive, like chat API sent, right? So that's the chat API application sending a message, and that's the recorded as a long span. I don't know why it's long, but it's kind of performance issues with the drivers. And then the other two spans, the tiny ones, are the two other services receiving this message. So even though it's a Kafka, it's a streaming application, sort of, or messaging at least, not streaming, you can still use tracing and investigate, and all the power of that like tool that I described before is still there. You can drill down and do the interesting things. So to summarize this, so a single trace is very powerful, rich source of data to investigate the behavior of a given request, right? You can, it tells the story of what happened for that request across all the microservices. And it's contextual. It allows like very deep drill down into what exactly happened at every step. And that's kind of, the more instrumentation you put in, the more details you will get. So it's like a knob you have to control it. You can think of it as a distributed stack trace sometimes, right? So this is one of the issues with microservices as you split the monolith. In the monolith, when exception happens, you get a full stack trace. You kind of know where the things happened. Whereas in distributed system, you just get one single piece of it. But trace gives you the stack trace back, essentially, across microservices. However, there are some issues with using that as to solve like all the troubleshooting problems. One of them is, well, it talks about a single transaction, right? Well, how do you know that that transaction is actually representative of anything? So yes, if it was a specific problem that you were trying to investigate, and that's the trace representing that transaction, then it's useful. But what if you're trying to analyze some performance issue? Let's say, like I said, users can take rides at Uber. What happened, right? So you drill down. You need to find out what causes this. And if you pick one transaction and it has some issue in it, that may not in any way correlate with the issue of the actual alert that you get, right? Another problem which you couldn't see in the previous examples is that, but traces themselves can get exceptionally complex. I will show some statistics soon. So this is an example, real example from Jaeger production at Uber. So it's, I think, driver goes online. That's like a type of request then when the drivers start their app, right? So we can see here that there's a, this doesn't work. There are number 30 services involved in that request. 200 spans, so it's about like 100 or more RPC calls in that request. That's a pretty big thing, right? So I couldn't display it, so I put a minimap at the bottom. You can see that's pretty complex structure already. So if you put it as a Gantt chart on the screen, then you'll have pages and pages to scroll if you want to try to actually reason about this thing, right? And that's not the largest trace at all, right? So here I have another, this is a heat map of our, like, in Jaeger production trace sizes at Uber, right? So we can see that, well, most of the time, we're kind of in a small ranges, but we pretty often get traces which are, what, about like 60, 50,000 spans in a trace, right? Occasionally we get 100 or 500. Sometimes we get this one with like whatever, 10 million spans in it. So what do you do with that? Like, how do you even visualize this thing or try to troubleshoot that? And so, I mean, there are various techniques of doing that. One is sort of more number-based, right? And actually, Facebook is doing that. So Facebook, they have an infrastructure very advanced because they've been doing tracing for like 10 years, where you can run a feature extraction on the two populations of traces, and then you compare them, like the performance characteristics, saying like, oh, on average, this call was here, but in this population, this same call is like taking twice as long, right? Across many traces. So that like removes the anomalies. Very good one. But one issue with that approach, well, maybe not issue, but like sort of going back to the observability versus monitoring, is that when you start talking numbers, that means that you are already looking for answers to questions you knew to ask up front, right? You decided that that number is going to be important. And I'm approaching it from what if I didn't know what to ask? Like, if I knew what to ask, maybe I even knew what to fix in the first place, right? Why should I have like the monitoring for this one? And so I really want to be able to ask questions that I didn't think I needed to ask up front, right? And that led us into a different direction with our tooling at Uber. We decided to explore like various visualization techniques that allows us to tackle complexity of like these traces in a different way. And so that's one of them is just taking a different representation of the trace. Instead of a Gantt chart, it's just a graph of RPC calls, right? May or may not be useful, but one thing that it's sort of vertically time ordered, so you can read it again as a narrative. These things happen in that order, right? And then another thing is that a lot of times services make repeated calls to each other. Like if you call in Redis, then like this is a previous example, the toy example, where it's like a staircase. There's 10 calls to Redis from one service. So in this graph, that's going to be just one single edge. We collapse the repeated edges because, well, while they're important if you actually drill them down, they're still there. It's just visualization. It's not like an aggregation. But in order to comprehend them, they're kind of just noise. They don't add too much to your comprehension, right? And so these are like basic techniques that they may not be exceptionally useful just on this graph, but we will keep using them for more visualizations that are helpful, that I'll show later. Another thing that we also tried is the color coding here, right? The color coding is, I think, by service, which again is not super useful. Although you can even imagine other color coding, maybe like if you color it by the type of technology used by the service. So you can say, oh, these are my Java services, these are my database services, things like that. That might be a lot more useful visualization than just a random sort of by service color coding. But the other type of color coding is a heat map or latencies, right? So here we essentially just use the red heat map to represent the longest duration of a span. And that gives you immediately a path to understand, well, if you're looking for latency in this trace, it's obvious where it is, right? Well, the top one is obviously the longest one because that was the experience. But if you kind of follow in, then this is the section where bad things happen, right? So you see that, and that's like your path to understand this. So that's good. However, it's not good enough. If you are imagine you have two versions of a software deployed, and one like the later version like has a bug, throws an error or something, right? How do you understand that? Do you just go dump the source code of that latest version and start reading it front to back? No, right? You look at the diffs, what happened between those two versions. That's the primary way to understand what changed in the code. And so diffs are actually a traditional way of looking at performance profiles and comparing them, right? If you are investigating a memory leak, how do you do typically? You take 2 snapshots and you compare them. And so that was natural for us to explore that, well, we can do that with traces as well, right? Which led us to that, a tool which just does a comparison of 2 traces, right? And you can think of it, okay, well, you pick a trace which is successful at a given endpoint and then a trace which failed. And then you compare them and you try to understand. Like, looking at one of them is very hard, like we said, it's like can be millions of spans in it. But comparison reduces that complexity a lot. And here is an example that I'm going to walk through. So I don't know if you can see that, but yeah, it's very small. But the left trace has 500 spans. The right one has 300 spans, right? So it's like already twice as large as that scary trace that I showed before for driver go online. And as I said, the same principles of graph constructions apply here. So it's like a chronologically sorted top-down, and repeated edges are removed. And then we do the structural comparison of this here, and we color code that structural comparison. So on number 1, we see a bunch of gray nodes, which means that they are present in both traces on left and right. So there's no change in the behavior. Then at the bottom, we see there's like a whole section in red, and the color coding is inspired by the code diffs tool so that everyone is familiar with it, which means like it's missing from the right, right? So like it's present on the left, but missing on the right. That's the red color. Then at the top right, we have like slightly light colors. Again, because the edges are collapsed, there might be differences in number of those edges, right? And so those colors, like light colors, represent, so this is like structurally they're similar, but there are some statistical differences in how many calls happen between these things. And finally, so the important part of that tool is that you look at this, you immediately see, okay, well, there's something wrong going on at the bottom of it because the whole swath of calls didn't happen. And so if you want to investigate the problem, that's probably where you should look for, right? This actually is a real production trace from Uber Eats application. So the order couldn't complete. I think transaction, like there was some problem with the credit card, so transaction rolled back, and therefore the whole section below didn't happen in a failed trace on the race. Right? So that's the explanation. One other thing is that, again, because this is just visualization, not an aggregation, you can go back to the raw trace and investigate, right? So we can go to the failed trace, and we drill down, and we can see, okay, well, these are the details, and this is like an exception saying you have outstanding balance. That's why the credit card check failed or something like that, right? We could have gotten here by looking at that trace from the beginning, but again, if that trace has, I don't know, 10,000 spans, then it would have been pretty hard. Whereas with the diff tool first, we narrowed down the place where the problem resides, and then we have a deep link from that going into the span details that you can drill down further. Another production story. We used to have like last year or maybe 2 years ago, we were doing the migration from one data center to another. And the data centers were nearby, right? So what I mean nearby, I mean in America, distance is measured in units of time, right? Like how far are you? I'm 10 minutes away. Right? So same here, the data centers were like a few milliseconds away. So when we migrated a whole bunch of services to the second data center, we were expecting latency to not be affected much. Like within a second, that's fine. But instead, we saw that the latency almost doubled. And we were trying to investigate why that is. And so we tried that difference tool that I just showed before, right? And that was the sort of the outcome, right? So there's like very similar structure, a lot of gray nodes, not a lot of changes, but then there is some sections. So here's the 2.7 seconds, and the right one is like 4 seconds. So that's almost 50% increase in latency, right? So when we look at the differences, is here okay, we see like a new section of calls being made, which is kind of strange. Why just moving services to microservice to data center? But we still don't know from this view whether these green nodes are actually responsible for almost like this massive increase in latency. Another option may be this whole increase is actually spread out across multiple nodes, because again, this view just doesn't show that. It's not built for latency investigation. And so as a result, we said, well, let's use the heat maps instead, and that's the color coding we already saw. And that became a lot more useful in this case. So we kind of saw that before, but this is the difference now between two traces. And so again, we have a section where there are no changes, similar durations between in spans, right? Then we have a section with like white nodes that saying, well, we can't compare it because that was the section that was new in trace B, so we kind of don't know what's going on there. But even if we ignore that, we can see that there is already a very clear path of where the latency was introduced, right? And so once we drill down into that service, we realized that when the migration happened, so like 3,000 microservices, you can't actually migrate all of them at once, right? It's a process. And so some of them weren't like migrated properly, and so that particular one was experiencing latency because of that. It was like starting making cross. It didn't understand as the configuration was messed up, so instead of calling locally within the data center, it was calling across the region and introducing these huge delays. And it was doing it very many times, so that was responsible for the issue, right? You can obviously mouse over and see the details. It says like what the percentage of latency increase. This one is the most responsible. This one is like about 50% of total latency. So you can also do another type of heat map as a sort of so-called self-time of a span, where you take all the time spent in the children, subtract it, and then keep that only as your like indicator for latency. That highlights the different types of issues. So to summarize, how these approaches are different from just a single trace, right? So one is like it surfaces a lot less information about the trace. We condense that information. And that allows us to actually comprehend the complex structure of a trace much better. And emphasizing the differences is really the key part, because when you investigate in performance, that gives you a lot narrower surface to focus than if you look at the whole thing at once, right? And finally, distinct comparison modes are very helpful because you can tune them to specific problem that you're investigating, and they're helpful more than that way. But there are some challenges with this one still. So I said that traces A and B, what are they? One is successful, another is unsuccessful. But kind of like, first of all, you have to pick the right baseline. What is a successful trace? And even if you pick one which had no errors, which looked normal, from statistical distribution, it may still be an anomaly that something wrong happened here. On average, it doesn't happen, right? And so you're comparing not necessarily the best things, right? So what you really want is comparing a trace versus some sort of average behavior of the system. That gives you a much better understanding of how that failing trace is actually different from the normal behavior. And for that, there is a next tool that I will present right now. And obviously, we have millions of traces in the database, so creating an aggregate of the behavior isn't that hard. So, by the way, up until now, I think all of that was open source in Jaeger. This new tool it's internal for Uber for now. We haven't spent time on open source. Here is the tool is specifically designed for root cause analysis. It uses slightly different color coding, and some other improvements, but overall it's still very similar, right? So we see that we have like a top-level operation and endpoint. There is like it's actually empty here, but you have a request and response that can contain like a payloads of the request. Sometimes very useful to drill down at the top outcome. You can understand what's going on, and also you can always go back to the raw data representing that trace. So if you want to drill down more on the details. Finally, missing nodes are represented in black. So again, our attention is immediately visually drawn to this place, saying, "Yeah, this is the area of the trace that something bad happened." Yeah, the color coding is different. The white is sort of like a no change, and red is reserved for like nodes with the errors specifically happening, because that's also sometimes very useful to look at. So this is a node that shows there's an error, and then there's actually 2 errors. So when you click on it, you get the details on the right that kind of describes what type of error was actually happening there. So this tool has been exceptionally helpful in the past few months at Uber, that once we rolled it out, like the first responders, when they go from the business metrics failing to investigating where the issues occur, they had anecdotes where, like, instead of 30 minutes now, they spent like 2 minutes to solve that thing, right? Again, to solve that biggest problem, that where the things are failing, not why. Like, in some cases, it tells you why. In some cases, it doesn't. But at least where is the very time-consuming thing. And very often, once you know where, you can already start to think of how to remediate it without even figuring out why it's failing, right? Because you can say, well, let's just bypass the service. Let's like reroute around it, something like that. So there's lots of opportunities at that point once you know where things are wrong. And so what is the main difference of this approach, right? It's like it's mostly like much broader context. You don't compare one trace with another where there can be like another one could be anomaly and not representative. You're really comparing with a population which is guaranteed to sort of smooth out outages. And the other one is that that tool was specifically built for root cause analysis, right? So there's like we're not trying to make it a very general purpose investigative tools or even performance. There's no performance analysis in that tool. That's just like outage mitigation as the first thing. And so, like my last section is complexity of microservices is not just about this sort of like communications of microservices. It's also about data complexity, because imagine of how much data actually goes through that architecture, and tracking that data is also important, and trying to understand where it goes. And Uber obviously is a data company as such. We compute ETAs, compute routes, so we use a lot of data all the time to actually operate the system, right? And so our typical sort of flow of data is that there's a lot of exchanges happening in the RPC space, then there is some asynchronous processing via Kafka messaging, and then in the end, some of that data ends up with like in the data lakes with HDFS. And so understanding that like the quality of the data can be very hard. And so if you have a Hive table and suddenly it's like it looks completely wrong, and you're trying to understand, well, where this data came from? Well, it came from this 500 transformations upstream, right? Well, you need to be able to trace that somehow. And tracing is not necessarily always like able to solve that, but it's part of the solution, right? So the solution is that we build a tool internally. I'm sorry it's too small, but it's just like conceptually you can understand. So on the left there's the RPC space, right? So something happening, the data is transformed. Then in the middle there is some Kafka stream. And then on the right side there's like a series of Hive tables, like Kafka ends up in one table as is, and then it gets transformed, more transformed, etc., potentially joined. So this tool actually looks at individual data elements, right? In this case, our focus was the Kafka stream, like how the messages in this Kafka stream, where they come from and where they end up, right? And so that's what the graph shows. You can refocus it to other things. You can also filter it down to specific data elements. Let's say, I'm not interested in the whole trip. I'm interested in, I don't know, the start point of the trip, like where that came from, right? And so you can drill down. And so the tracing part here is really the RPC space and some partially Kafka space. But the Hive transformations, those are done more with the static analysis of like the relationships between tables. I mean, tracing sometimes like has a problem with that space because of tracing works when you have a very well-defined transaction. When you start like joining and aggregating data, then the notion of a transaction becomes very vague. So you're actually combining a lot of different data. And so tracing naturally stops there. You can't really model that on just on a logical scale. And just to close this quickly, all of this is only possible if we have very high quality instrumentation in the systems, right? And instrumentation is actually the hardest part of tracing. Getting it in there and collecting data is hard. Building tools is the easy part. And today, all our software is very highly composable. We tend to use a lot of open source frameworks in our application, right? So if you have a microservice, you probably have some server framework that you use. You have some RPC framework to make calls downstream, some database drivers, some message drivers. So if we want to trace all of that, we need instrumentations at all those components. And that instrumentation needs to work together. But if they're open source, well, sort of like you need some sort of a standard to actually have them speak the same language, right? Because if they don't, we have traces which come into your service and die, and then the next trace goes out of your service. That's not what we want. We want the continuity of the trace, right? So, and I want to just call out to two projects that are happening in the industry today. One is an OpenTelemetry, a new project announced at CNCF. It's a next iteration of two previous projects, OpenTracing and OpenSensors, if you've heard of those, right? So those two projects decided to merge efforts and basically become one single standard rather than competing standards. And the other one is in the W3C, there's a working group which works on the data formats for tracing. That includes like how you pass data between processes, so-called trace context. And in the future, it will also include how you send traces out of process. That's like early work started, but hasn't been done a lot of it. And to summarize, distributed tracing is definitely one of the most helpful tools for, well, observability tools at least, for understanding and tackling the complexity introduced by microservices. Visualizations are an important part of that because the tools itself collect so much data that it's very hard to just look at that data in the raw format. So visualizations help our visual cortex to process that data much quicker and sort of narrow down things that are important out of this mass of data. And finally, distributed tracing, I personally think we just scratched the surface with that because we think that it's going to be sort of like a core driver for automating a lot of our operations with microservices, because that gives us like unparalleled insights about how our architecture operates in reality, right? So we have engineers who design those systems and they think they know how the system works, but I mean, the system like behaves the way it wants to behave, right? And when we have so many services and all the interactions happening all the time, so tracing monitors that in real time. It gives you a very accurate picture of what happens today and not what you thought you designed in the system. And that's my talk. Thank you very much. And if you want to find me on social media, I have it on the website.
So we have time for questions. Does someone have a question? In front.
Hi, thanks for the talk. With OpenTelemetry combining OpenSensors and OpenTracing, which API is going to choose?
It's a new API, but it will provide backwards compatibility shims for both of those. So the existing instrumentation would work with OpenTelemetry.
Thank you.
Another question?
Thank you for your talk. I have a question. Do you use some sampling strategies for specifically in Uber, or you trace every single request?
Yes, we do sample all the requests.
And what is the reasonable sampling configuration?
It's actually very varied because we have adaptive sampling, which is sensitive to the type of service and the traffic that service generates. And so if you have low QPS service, we will sample probably 100% of it. Okay. If it's a very high, then it's going to decrease that.
And what is operational, like say, complexity cost to manage all these traces, store this data?
There isn't much. I mean, it kind of depends on how well you have infrastructure supported in terms of storage, because we had a bunch of issues with Cassandra. We had to manage it. Once we moved to manage Cassandra by another team, sort of the operational challenge went away for us. Almost. So yeah, it kind of depends on the maturity of the organization more than the tracing technology by itself is not really that hard. So we depend on Kafka and Cassandra. Those are our main dependencies.
Okay, thank you.
Mm-hmm. Hi, Diana. Thanks for the talk. What's your assessment on the current maturity level of the distributed tracing within the Uber?
Could you repeat that? I didn't get it.
What's the maturity level of distributed tracing within Uber?
Maturity level? Well, how do you define maturity level? Like adoption or? I mean, so I think there are several things here. Like adoption is what I count as adoption is how many services actually generating traces, right? And so we're probably like 70%. So it's pretty high, but it's very hard to get to the long tail because we started tracing when there's already a lot of services. And so like, you better start when you just design the microservices architecture. So I actually, in my book, I have a whole chapter about how to do that right, like, because we didn't. And so you want to, like, there's a lot of sort of steps you want to take up front to make sure that this is sort of sustainable process, right? But another aspect of maturity, I guess, is like how much usage the tracing gets, and that I think we're still pretty new to that. I mean, what's interesting is that performance, like tracing was originally created to solve performance problems. Like people think, oh, this is for latency investigation, right? And that was not the use case at all at Uber, ever. Like there's probably like a few, I don't know, power users who use that for latency optimizations, right? I've seen examples of people doing that. But by far, that's not what Uber uses trace for. It's for that. It's for understanding the complexity, for root cause analysis. It's basically dealing with the microservices complexity, rather than, oh, I want to sort of like start optimizing performance. I guess Uber is still a young company. We probably haven't reached the maturity where we actually like need to drill down into performance issues that much.
Do we have another question?
Over there.
Oh.
Thanks for the talk. I have a quick question there. In an async call.
Speak up, please.
In asynchronous call across the systems, how is the tracing metadata passed along? Is it part of the payload or?
So yeah, I mean, it can be, but like internally at Uber, I strongly advised against that. And so what we're doing is we upgraded Kafka to 1.1, which supports records headers, right? And so it passed, the tracing context is passed in the headers so that you don't touch the payload, the business payload. Because otherwise it's like deploying it becomes much harder if you introduce it in all kinds of various business payloads, right? And so it's the same, basically, metadata headers is the same principle as works for RPC calls in HTTP, et cetera. So I would recommend to stick to that.
So if you have different messaging system, you would have to have custom logic to pass along this metadata, or it comes?
No, there's no customer logic because people use like standard drivers to write messages to Kafka, let's say, right? And so that driver has an instrumentation, a middleware in it, which says, I'm going to take tray context and package it into the record headers.
Cool, thanks.
Mm-hmm.
So we have time for one other question. Do you have another question? OK. So then thanks a lot, Yuri, for your awesome talk, and give him a warm round of applause.